Yeah, good morning, students. In the previous class, we had a discussion on what are the different operations we can perform on a data structure. Fine. Now, in today's classroom discussion topic, we would like to discuss on how to compute the space and time complexity of a given algorithm. Fine. So now I would like to share my screen. Hope my screen is visible to you. Fine. So this is week one, lecture three. Topic is time and space complexity. So summary of the previous classroom discussion topic is that operations performed on the data structure we classified as these traversal, searching, sorting, merging, insertion, deletion, etc. These are the different operations we can perform, and the identification of the various data structures which are suitable in our real life applications we did in the previous classroom discussion topic. Fine. Now, coming to this lecture objective of this today's session is that this particular session will develop the students' knowledge on how to compute the space and time complexity. How do we calculate for a given algorithm? Fine. So the outcome of this session is that after completion of this session, students will able to compute the space and time complexity for a given algorithm or the code. So what do you mean by space complexity? Space complexity of an algorithm represents the amount of main memory required by the algorithm in its life cycle. So how much amount of main memory is required? So how much amount of main memory, okay, that is required for this particular algorithm. So the space required by an algorithm is equal to the sum of the two following components. One is a fixed part and another one is a variable part. So fixed part in the algorithm, that is a space required to store certain data or variables, so that are independent of the size of the problem. For example, simple variables and constants used program size, that is a fixed part. And the variable part is a space required by variables whose size depends upon the size of the problem. For example, dynamic memory allocation, recursion, stack space, etc. Fine. So now space complexity of SP of an algorithm P is given as C plus S of I, where this C is a fixed part and S of I is the variable part of an algorithm, which depends upon the instance characteristics I. Fine. So following is a simple example that tries to explain the uh, concept of this space complexity. For example, you consider an algorithm sum of a comma b. So this is what we are calling it as here, the algorithm to calculate the sum of a plus b. So c equal to a plus b plus 10. So we are computing this. So here we have three variables involved in this particular algorithm, a, b, c. Okay. And one constant, which is a 10 value we have. So hence the space complexity, we can take it as 1 plus 3. So now the space depends upon the data type of given variables and constant types, and it will be multiplied accordingly. Then next, coming to this time complexity of an algorithm represents the amount of time by the algorithm it takes to run it to completion. So time required for a numerical function, it is represented or T of n can be measured as the steps are provided. Each step consumes some constant time, and we are trying to compute, or we are trying to formulate a formula in terms of the time requirement. Okay. So for example, addition of two n-bit integers takes n steps. Consequently, the total computational time T of n is equal to C into n, where C is the time taken for the addition of two bits constant. Okay. So here we observe that T of n grows linearly as the input size increases. Fine. So generally, the time required for an algorithm to compute, to execute, generally, it will falls under three important categories: best case, average case, and worst case. So the best case is the minimum time required for program execution. Average case is the average time required for program execution. Worst case is the maximum time required for program execution. So we will measure the time complexity of an algorithm in three different situations. So minimum time, how much it is required, average time, how much it is required, and the maximum time, how much it is required in the worst case. So best case, average case, and worst case, these are the three cases we will consider to evaluate the time complexity of an algorithm. So if a function is a linear without any loops or recursion, so the efficiency of that algorithm or the running time of that algorithm can be as the number of instructions it contains. Fine. If an algorithm contains loops, then the efficiency of that algorithm may vary depending upon the number of loops and the running time of each loop in that particular algorithm. So we have different types of loops we are using here. So the first case is here is that linear loops. So to calculate the efficiency of an algorithm that has a single loop, so we need to first how many number of times that statements within the loop will be executed. So for example, consider this loop for I equal to 0, I less than 100, I plus plus, and then here we have a statement block. So here 100 is the loop factor. That means we already said that the efficiency is directly proportional to the number of iterations this loop is going to be executed. So that is what we are calling it here. So this statement block will be repeated 100 times here. So generally, the general formula in case of linear loop, we can say it as f of n is equal to n. This is the function we are considering for a linear loop. So for example, if you consider for I equal to 0, I less than 100, I equal to I plus 2. So here the number of iterations is half the number of loop factor. So here the efficiency can be given as f of n is equal to n by 2 instead of n. Fine. So which is an example for linear loops. Then second category of the loops, which we are calling it as the logarithmic loop. If we have a logarithmic loop, how the time complexity can be computed. So the loop controlling variable is multiplied or divided during each iteration of the loop. So like this is a loop controlling variable. Here we are multiplying that loop controlling variable I by 2. Here the loop controlling variable I we are dividing by 2. So like this, if the loop controlling variable is involving multiplication or division, then that particular loop which is going to be involving this logarithmic computation. So therefore, putting this analysis in general, we can conclude that the efficiency of the loop in which iterations divide or multiply the loop controlling variable can be given as f of n is equal to log n, which is called it as a logarithmic complexity. Then the third category here we have a nested loops. So the nested loop is nothing but loop within a loop. So loops that contains loops are known as nested loops. In order to compute, we need to determine the number of iterations the inner loop is going to be executed, as well as the number of iterations the outer loop is going to be executed. So both will be multiplied, then we'll get the time complexity for the nested loops. In this case, we analyze the efficiency of the algorithm based on whether it is a linear logarithmic or whether it is a quadratic or dependent quadratic nested loops. Okay, so these are the three different categories of nested loops in there: linear logarithmic, quadratic, and dependent quadratic. Fine. So linear logarithmic loop, if you consider that this is the following code where we are having this for I equal to 0, I less than 100, I plus plus, for j equal to 1, j less than 10, j is equal to j star 2. So in more general, this particular inner loop is logarithmic and outer loop is linear loop. So linear logarithmic nested loop, which we can call it as, so its function is f of n is equal to n into log n. Fine. So the inner loop is controlled by an outer loop. Then quadratic loop here, the outer loop is repeated 10 times, as well as the inner loop is also repeated 10 times. This is a quadratic here. That means the efficiency is 100 into 10 into 10, which is equal to 100. So in general, if it is a quadratic, here we have f of n is equal to n into n. Fine. Then another coming to this reflection spot here. So you have to compute the time complexity for the following code snippets A and B. Here in this A, anyone can answer this question? So how many times this loop is going to be repeated? Yes, exactly n times. This coming to the B question. So it is depending on this outer loop is repeated linear and inner loop is here repeated based on that dependent. Okay, so it may be taking it as what we can call it as n. Okay, if it is I, okay, so dependent quadratic dependent loop here it is called it as. Okay, so based on that here we are able to get n into n, we can get it as order of n square, also we can get it as. Fine. So if you are not able to answer this, please go back to this video and please listen to this video to get clarified this particular answer to this question. So the lecture outcomes are revisited here. After completion of this session, students will able to compute the space and time complexity for a given algorithm or the code. Fine. So summary of the session is that the space complexity of an algorithm represents the amount of main memory that is required, and it is nothing but some we have a constant and some are variable. Fixed part will be there and some variable part will be there. Combination of that gives the space complexity, how much memory it takes, and it depends upon the data types the memory are required for that algorithm will depends. And the time complexity of an algorithm represents the amount of time that is required by the algorithm to complete its execution. So time complexity of a linear loop may be f of n is equal to n, and logarithmic loop may be f of n is equal to log n. Nested loops, linear logarithmic, we have n log n, and quadratic loop f of n is equal to n square. This is fine. So this is what the summary of the today's session is that. So this is a lecture level practice problem. Show that 4 into n square, 4 into n square is equal to order of n cube. Fine. So try to solve this problem. So coming to this further readings here, this you can refer this classic data structures by the Samantha for further reference. Okay. So thank you, Vanessa.